Hello and welcome to In Control, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. I'm your host, Alberto Padoan, live from a recording studio in Zurich. Quick thanks to our sponsors, the National Centre of Competence in Research on Dependable Ubiquitous Automation, the International Federation of Automatic Control, and the IEEE. Our guest today is Bassam Bamieh, Professor of Mechanical Engineering at the University of California, Santa Barbara. Welcome to the show, Bassam.
Thank you. Thank you, Alberto, for having me. I've been listening to the In Control podcast for the past couple of months, and I've been really enjoying it. So thank you very much for having me.
This is a huge compliment. And also, I should say that I really was looking forward to recording this episode because I feel that your research really touches on some of the most important questions of control theory, at least today, in my very, very humble opinion, such as locality, how to do optimal control in distributed systems, and I hope we do touch on all of these aspects today. I was wondering, Bassam, where did you grow up and how did that affect you scientifically and what you became also later?
So I grew up in many places. I was born in Jordan, in Amman, and then when I was very young, 7 years old, my family moved to Lebanon, grew up in Beirut. But then during the 70s, late 70s, there was a civil war in Lebanon. So we moved around quite a bit. I spent 1 year in school in Alexandria and another year in school in Athens and then another year in school in England before I went to the US for university. So my school education was really quite varied. By the time I went to university, I had gone to 8 different schools in 5 different countries. So it was, in a way, it's an enriching experience because you get to learn many different educational systems. I have to say I learned a lot and my passion was science and math from early on, but mostly learning it from books from outside of school. So popular science books, and then the encyclopedia, for example. There was 1 year during the civil war in Lebanon where we didn't go to school at all. So that was a year off. And I think I spent a lot of time reading the Encyclopedia Americana at the time. And so I spent that whole year reading it. So I got a lot of education from books outside of school. But particularly physics and math were the subjects I was passionate about later on in high school. And so when I went to the university as an undergrad, I was trying to decide whether I should study physics or electrical engineering, and I ended up studying both. And I didn't really fall in love completely with mathematics till graduate school. You know, I liked math from the beginning, but seeing mathematics in graduate school kind of was eye-opening. Learning algebra and geometry, differential geometry, and group theory. These are subjects that I thought were fascinating.
I found very, very interesting the fact that all countries that you mentioned, many of them spoke a different language everywhere you've been, or at least more than one language. I'm thinking about Lebanon, but also Athens, England as well. Everybody with a very different culture. So that definitely, I'm sure that it contributed to shaping a very open-minded person.
Yes. I discovered that it doesn't matter where you go, people are fundamentally the same. Their deepest desires and feelings fundamentally are roughly the same. I mean, within any country, you have people who could be either right-wing or left-wing and that seems to be consistent across countries. It's not the country that makes the difference. It's within the differences within each country are the same, in my opinion.
I thought that we actually could start taking, as you say in your Control Systems magazine interview, the Scenic route. I read that you started in controls taking, as you say, the Scenic route through grad school, because initially you didn't actually want to do control theory. Is that right?
Yeah, I mean, when I finished my undergraduate was a double major in physics and electrical engineering, and I was debating whether to go to graduate school in physics or electrical engineering. And I'm glad I chose electrical engineering, even though I love physics. But I went to an undergraduate school that didn't really have much of a research component, so I really didn't know what to expect in graduate school. So it was almost kind of a bit of a random choice. I liked digital logic and digital hardware, and I liked systems and signals as well, but I thought maybe I'll do a PhD in computer engineering. Microprocessor design was something I was fascinated with at the time. And then after one semester at Rice University, where I started graduate school, I took signal processing, a graduate course in signal processing, and I just thought that is really what I'd like to do, is signals and systems. And then I ended up doing a master's in pattern recognition, image processing, and then I was also taking courses in systems theory with Boyd Pearson and Tanis and Toulis and mathematics courses. And then I became much more enamored with systems theory and controls because of just the beautiful mathematics, the idea that it's sort of a unified theory for all possible systems, whether they be mechanical, electrical, chemical, etc. I thought that was very fascinating. So I took a year off to work in a startup that was also doing sort of image processing, building ophthalmic equipments. And then after that, I realized I really want to do a PhD and do research. I don't want to be in industry. And I came back to Rice and I started a PhD in control theory.
Yeah, as a matter of fact, I was actually, of course, doing my homework for this podcast. I was reading that your first paper is actually not in control, but it's on object recognition with Rui de Figueiredo. Is that right?
Yes. I was actually going to do a PhD in pattern recognition, image processing. And then there was this theory of moment invariance for object recognitions, which was, to me, very beautiful. So I think we'll come back to this. I've been fascinated by invariant theory throughout and the use of symmetries and invariants to characterize various phenomena and as a mathematical analysis tool. So we had this work on trying to recognize an object, a 3D object, regardless of orientation. And if it's a polyhedral object, then you can show that there are certain quantities of each of the the images of the facets of the polyhedron that remain invariant in 2D for rotations in 3D. So that when you have parallel projection. So in a way, that was really sort of a nice piece of mathematics. It connected with object recognition. And so it doesn't really have much connection with control theory, even though underlying it, invariant theory does have connections, which maybe we'll talk about later. But that work was, I presented at a conference, the robotics conference, I think. That was my first conference. And at the same time, I was looking at what my colleagues in grad school, namely Manzar Dahle, was doing in his thesis in control theory. And the conference I went to, International Robotics Conference, this was back in 1985, I think, where I presented this work. It was, back then, it was, still is probably, the conference was like the Wild West. So people were doing simulations and so almost anything goes, right? And so I felt intellectually lost in the sense that, there are people doing a lot of computational experimentation and there isn't really a body of theory that connected it together. While when I saw control theory, it was quite the opposite. And that's what attracted me to it. That's what made me make the switch.
Especially for somebody who's so enamored of physics. So the possibility of establishing a grand unified theory or something that speaks to every domain of physics is probably very fascinating.
To me, that is really the core of control theory, is one of the important cores. It's, feedback is important, etc. But the fact that you are able to do a analysis of a variety of physical systems. People working in dynamical systems say the same thing. And control theory also addresses that. And to me, that is probably the most attractive part of this theory.
You brought up many important points that I hope to bring up also in this discussion. First of all, as you said, the concept of invariance. This seems to be one of the defining threads throughout your career since the inception, as you say, in this first paper, all throughout. Another point you brought up is the interaction with Munzer Dahle and also that with Mustafa Hamash that we will bring up at some point, I hope.
Yes.
With your advisor, Boyd Pearson. And yeah, as I said, also this fascination for physics. I don't know where do we want to go from here. I personally found quite fascinating the fact that, as you said, you started your PhD at Rice in 1985, from what I read in the records, and you had two fairly important colleagues in the context of control theory. So I was wondering, what is it so special in that specific region of the world, or in general in the Middle East, that brings up so many good control theorists out there?
I think it is maybe a bit of a coincidence. So I started at Rice at 83, actually, which is the same year that Munzer Daleh started. But as I said, I was wanting to do a PhD in computer engineering. And then later on, Mustafa Kamash also joined the program. And then I switched advisors to Boyd Pearson afterwards. So all three of us were there at the same time. It was, very intellectually very stimulating. We used to have daily discussions about everything, not just control theory. So in some sense, maybe it was kind of a mutually reinforcing intellectual environment. At the time, also, Rice was the electrical, engineering department graduate program was very intellectually stimulating. We were treated very well as graduate students. And so it was really an intellectually stimulating environment. And later on, Muhammad Daleh, who's the brother of Munzer Daleh, who passed away sadly many years ago, also was at Texas A&M as an assistant professor. And so he worked in control theory as well. So in some sense, all four of us were really very engaged as very good friends, but at the same time also sort of researchers that were bouncing ideas back and forth all the time. So I think it was a very, very stimulating environment that way.
It's kind of incredible to think about, and such a critical mass of control talent was all in Texas at once. It's very, it's very fascinating.
Even though now we have all sort of gone in different directions in terms of the kind of research we do, still the core of control theory and that way of thinking about problems, I think is a constant.
This is something that I was actually thinking about in preparing this episode, that you three or four spawned in very different directions, all making very important contributions in different areas of science and engineering, but with sort of, I would call it an input-output or a robust control mindset. But okay, this is something that I hope we'll talk about soon. So the topic of your PhD was mainly dealing with the relationship between continuous and discrete time, maybe. I wonder whether this is a fair description of the subject of your PhD, together, of course, with robust control.
Yeah.
So we are located in time as you said, in early 90s, end of the 80s, I would say.
You're right.
Second half of the 80s.
I think I got interested in this problem late in graduate school. I was working on L1 control theory at first, and then this problem of sample data, as we called it at the time, sample data systems, came up because people were doing robust control designs and for time invariant systems, continuous time and discrete time. And then the idea of when you actually implement it, this really came from sort of a practical considerations, which is if you implement a digital controller, even though in discrete time, the digital controller is discrete time invariant, continuous time plant is continuous time invariant. When you put them together through analog to digital converters, the continuous time closed loop, which is really what you care about, because that's when disturbances are entering in continuous time and regulated variables are continuous time signals, that closed loop is actually time periodic. And it's time periodic with the sampling period. And so if you're sampling very, very fast, it is not so much of an issue. But if the sampling rates are compatible to the time constants of the plant and or maybe even 5 to 10 times faster, there may be issues. And there was actually earlier work that motivated this problem. And that was done by, I believe, Alan Tannenbaum and Kameshwar Pula and Kargonikar, where they were looking at the gain margin problem. And then they showed that with digital control, so sample data control, or when you discretize the plant, you can move the zeros, actually, the non-minimum phase zeros in discrete and continuous time. So certain choices of sampling times, they can be minimum phase.
Oh, wow.
And then the idea is that then you can have infinite gain margin. So let's try to design a discrete time controller to do that. And, people were doing that. And then they discovered that at the discrete time instant, the response looks great. But if you look in continuous time, in between the samples, it's doing crazy things, of course, as you're trying to push that gain margin very high. And so then the idea that you should really worry about intersample behavior became sort of more popular. And that was sort of the impetus for the work, where you try to analyze the full continuous time system as a time periodic system, and then optimize the performance of that. So periodic systems can have really very rich behavior. Maybe we can talk about that a little bit later on.
Sure.
Because even linear periodic systems can exhibit things like parametric resonance, or vibrational control is kind of it can be thought of in that way. But in the sample data system, where you have a digital controller connected with analog to digital converters, there's a very special type of periodic behavior which is actually easier to characterize. So the work we did basically allows you to do optimal design for the combined hybrid digital and continuous system. I used the term hybrid at the time. Now it means something different, but I meant the hybrid continuous discrete time systems. And turned out you could actually do it fairly. You can get very detailed formulas for the design, 2 Riccati equations for the H2 and H infinity problem, and so on. And this was a time when many other people were actually looking at this problem. Shinji Hara and Pierre Kabamba wrote, had a solution to this problem. Yutaka Yumamoto also developed this lifting technique, which I also developed independently. And then Tong Wen Chen and Bruce Francis were working on this. So and Tong Wen Chen actually wrote a book on this a few years later, which is a very nice book to summarize that work. The irony is that because you can sample very fast and process, you can implement a digital controller at fairly fast timescales, much faster than most plants. It turned out that it's not really that important to do that kind of design. You can just simply discretize the controller that you did with a continuous time design, which is most people's preferred method. And provided you sample fast enough, the discretization you did, even though not completely optimal, is pretty close. So it turned out that theory, even though it was motivated by practical applications, is really only consequential in very, very special cases where you have limitations on the sampling rates and so on.
And how does that fit also in the L1 optimal control context that you mentioned at the beginning? Or is there a relationship?
Well, it doesn't. In a way, it was kind of independent. I did the L1 version with Munzer Dörfler on the L1 version of the sample data problem. That solution turned out to be not as nice as the H infinity and the H2 solution. It required essentially a kind of multi-rate sampling for approximation. There was a fundamental reason why the solution in the H2 and H infinity case became very compact and very precise and easy to write down, and that's because of the Hilbert space structure. While for L1, because of the Banach space structure of the norms, sort of a simple way to say it is that these unit balls became arbitrary convex sets, which are, do not correspond to a finite sort of discrete time L1 problem. So that solution is just not as nice as the H infinity H2 solutions.
I must confess, actually, I'm a bit ignorant on the motivation behind why would one want to do L1 control.
Oh, that's a great story. So the idea, I think it was popularized by Vidyasagar at the time, around the time of H infinity. And the idea is that if your disturbances are L infinity, that is, you only know bounds on the size of the disturbances and the disturbance signals, and you want to put L infinity bounds, so just maximum bounds on the, say, regulated variables. So that's the L infinity to L infinity induced norm, which you can show is the L1 norm of the impulse response. So that problem was kind of open for a couple of years, and then Munzer Dörfler in his PhD thesis used duality theory to show that the properties of the optimal solution. And ironically, that was he showed that the optimal closed loop is FIR, and also kind of sparse, the number of non-zero components in the closed-loop impulse response, optimal L1 closed-loop impulse response, is no larger than the non-minimum phase zeros of the plot. So in a way, it sort of predicted or sort of the precursor to all of the sparseness promoting uses of L1 that we are aware of today. In that context, in the mid-'80s, it was basically showing that the closed loop is also sparse in an FIR sense.
Super interesting.
So the L1 problem came from a practical motivation, which is you know nothing about the disturbances except their maximum amplitude. And if you were interested in regulating things with a maximum guarantee, that was potentially one way of doing it.
I was actually having discussions with John Doyle at the margin of our interviews earlier in other episodes, and he was actually advocating that that's a very good way of doing controls even today, precisely for these sparsity issues or improvements that you were mentioning.
I think that in particular in the context of distributed control, that also makes more sense today.
Yes, I'm actually looking forward to to talking about that. Before I do that, I just wanted to do justice to also the body of work that you contributed to creating before moving towards the spatially invariant domain. I was also wondering, so before you mentioned essentially periodic systems do exhibit very rich behaviors, I did also note here another publication that piqued my interest in doing my homework on the identification of linear parameter varying models with Laura Jarre. I don't know what you had in mind that you wanted to talk about in relation to this context.
Yeah, I mean, this is actually the problem came from Laura Jarre, who was doing system identification at the time, and then we thought about doing linear parameter varying systems, which is it's a practically motivated problem, right? So linear parameter systems in the context of gain scheduling are very widely implemented. And so the idea is that if you want to do system ID to basically derive a family of LTI models, which is what linear parameter systems are, often the idea is that you set the parameter, the gain scheduling parameter fixed, you do LTI identification, you increment it, and you do it, you do a whole series of such LTI ID problems. And then we thought, can you do it all in one shot? Can you change the parameters rapidly and do the ID in one shot, provided you have enough data? And the answer is yes, you could do it. And we came up with persistent safe excitation conditions for that identification to converge.
I thought that was actually quite, in English, I would say that it's something that is quite actual, meaning that in the data-driven control literature, people are now wondering how the hell do we do data-driven control in an adaptive fashion without making assumptions on how quickly or certain parameters vary or the behavior of the system varies. And, and actually in the end of your paper, you do have this quote on persistency of excitation having a natural interpretation of basically visiting regularly certain points that you need to visit to make sure that the LTI models that you need to identify are actually identified.
Yeah, the condition is very intuitive, right? So if you do it the traditional way, you fix the gain scheduling parameter and then you do LTI identification, you go again to a different gain scheduling parameter and you do all of that. If you do it in one shot, for example, say you're cycling through the gain scheduling parameter, you just have to visit every point infinitely many times, in terms of the sort of asymptotic convergence. But basically, it is a very intuitive persistence excitation condition. You just have to keep coming back to that operating condition often enough.
So here I actually glazed over on the fact that we moved forward. We are now in the 90s and you're already at University of Illinois, Urbana-Champaign. I don't know if that also complies with what you know about your life. At least based on my research, that's what I found.
Yes.
I have seen that you did work also on tokamak plasma control, basically. I found that very, very fascinating.
I was always, fascinated with physics problems. And there was, at the University of Illinois, I was there for 6 years after my PhD as an assistant professor in ECE. They had a very good nuclear engineering department. And then one of the leaders in fusion research, George Miley, Him and I talked about plasma position control in a tokamak. We did a numerical, basically, experiment. It's not easy to implement these things on a real tokamak. But so we applied basically H-infinity control for vertical plasma position stabilization. And this was published in Fusion Technology. And, I've always been fascinated by tokamaks because I think it's a problem that has control all over it. But the people who are doing research in that area are adopting feedback control very, very slowly in time. Now it's more common to talk about control for tokamak reactors. Plasma, basically positioning the plasmas in a way that, prevents it from running into the walls and so on. The amazing thing about plasma dynamics is that it is so unstable. So plasmas always want to run away from you. They have so many modes of instability, but a tokamak reactor is full of coils that you can also control. The coils can read off information about the plasma, and they can at the same time actuate. So a tokamak reactor is it's full of feedback control loops that you could close, but the people are closing them very, very slowly over decades. So I think that's probably one of sort of open distributed control problems that can have significant impact.
Was that your first interface with the fact that this is a distributed system, or did you have other experiences before?
It made me think about distributed control, but the problem that we did with George Miley and his student was really not a distributed control problem.
I personally have no knowledge or experience with tokamaks, but I had just a curiosity on my side. So how far you think we are from an actual implementation? I mean, I know that there are experiments out there, but rather I should say deployment in the wild of tokamaks.
I'm probably the wrong person to ask this because I haven't kept up with the field since then. My impression is that this area is really ripe for interaction with controls. And that's been happening. You will see papers at the CDC about plasma control, more and more. There is a big barrier to entry. So you have to learn fluid dynamics and plasma dynamics, magnetohydrodynamics, MHD, which combine the Navier-Stokes with Maxwell's equations, or maybe Euler's equation if you're in a sort of a low density regime. So it's, there's a big barrier to entry, but if we talk later about the work we did with Navier-Stokes, I can explain why that barrier seems higher than it really is.
Actually, yeah, let's move on. Let's talk about spatially invariant distributed parameter systems. I must say that actually the fact that we're going to talk about PDEs, and every time I see PDEs, personally, I think, abandon all hope who you enter here, like in Dante.
Yes.
But in reading your papers, I actually had the opposite feeling. So you made me almost think that PDEs are easy, because, all my friends that who study PDEs normally are always obsessed with regularity, smoothness, well-posedness, and then you never really end up talking about how do you actually use them in the wild. But with the papers that I read from you, gave me really the opposite impression. So these are actually beasts that we can tame, especially with our control theoretic tools.
Thank you. That's a huge compliment, because my idea was that, PDEs are no more difficult than standard systems. We should talk about infinite dimensional systems and finite dimensional systems in the same breath. And I feel strongly about that. And I think there are historical reasons for why infinite dimensional systems within control theory have been viewed a certain way. I think a lot of the work originally came from researchers who came from the applied math community, looking at regularity and the semi-group theory of regularity and well-posedness. And in any research area, you really have a wide selection of questions you can ask. So, what distinguishes somebody, say, doing a particular style of mathematics versus somebody doing a particular style of engineering is not so much whether it's deep or shallow. It's just which questions are important to you, right? So I felt that with semi-group theory and regularity, these are things that can be important at times. But the way that I thought the literature was written is that by the time you're done checking regularity and smoothness and well-posedness, you're exhausted.
Yes, I can relate to that.
and then you can't move on to what I consider to be the really interesting questions, which is structural questions, right? So in a distributed control problem, how far does information travel? How far do disturbances travel? What should be the architecture of the controller? These were, to me, the questions that were structural questions that I found more interesting. And people make a big issue sometimes about the difference between infinite dimensions and finite dimensions. I like to say that if your theory has a discontinuity at infinity, if the infinite dimensional case is dramatically different from a large finite dimensional case, that means there's something lacking in the theory. Maybe you're not asking the right question. And I can give a concrete example of that. Maybe I'll do that right now.
Sure.
But I think this is a very important point. So typically, the example that's given for the difference between finite and infinite dimensional functional analysis or linear algebra facts is the shift operator. So if you take the infinite matrix that represents the shift operator, it's a matrix with just, say, ones on the subdiagonal or the superdiagonal. And if you truncate that, what you get is a Jordan block. And a Jordan block with zeros on the diagonal, that has as its eigenvalues just zero, repeated many times. But if you go to the infinite dimensional shift operator, its spectrum is the entire unit disk. So it seems like there's a discontinuity at infinity, right? Any finite truncation of this gives you eigenvalues spectrum at zero, but the infinite dimensional object has a spectrum, which is the unit disk. Well, that's all true. It doesn't mean there's a discontinuity at infinity. It means your measure of continuity, which is the spectrum, is a fragile object. So, for example, if you take that matrix and you make it the A matrix of a system, and then you look at the resolvent, which is sort of a transfer function from input to state. So if instead of looking at the matrix, let's call it A, which is a truncation of the shift operator, you look at SI minus A inverse, which is the resolvent or the transfer function, you see that there is no discontinuity. If you look at the level sets of the resolvent, if you look at the transfer function itself, it behaves continuously as the size of the matrix goes to infinity. So the spectrum is a fragile object because, again, if you think about this notion of the pseudo-spectrum that's been popularized by Nick Trefethen, which is really related to stability margins in robust control. If you take, instead of the matrix, you take the matrix plus delta, you let the norm of delta be less than epsilon, you look at the spectrum of that, you kind of thicken the spectrum. And that's a more robust way to think about the spectrum than just the point spectrum itself. So this example that's given always as the signature of a discontinuity at infinity, meaning things at infinity are different from very large scale systems, it's really dealing with a fragile object. And that means that object, which is the spectrum, is not the right thing to be looking at. You should instead look at transfer functions or system norms or something else that is more robust.
And here you can feel all the heritage of robust control echoing in this wonderful journey.
So related to this is so the work by Nick Trefethen and his group at Oxford and many others. He wrote this beautiful book called Spectra and Pseudospectra. I'll tell the story because it's really fascinating. So and he comes out of the numerical linear algebra community. And the genesis of this, as far as I know the story, is that there were certain algorithms that iterative algorithms in numerical linear algebra that were proven to converge in the sense that the analysis was basically a linear time invariant discrete time system, and you can look at its corresponding A matrix and show that all of its eigenvalues are within the unit disk. Therefore, the algorithm ought to be convergent. But it doesn't really work in actual implementations very well. And so what Trefethen and company showed is that even though the spectrum of that matrix is inside the unit disk, if you look at the pseudospectrum, so instead of looking at the spectrum of A, you look at the spectrum of A plus delta, delta norm is epsilon less than epsilon. Those, when you look at the pseudospectrum, which is that whole set, it goes outside the unit disk. So with slight perturbations, which you will always get in numerical algorithms from round-off error and discrete representations, the algorithm in practice is not convergent. It's unstable. So that led to a whole selection of results related to pseudospectra in other areas. And in fact, my foray into fluid dynamics came from reading one of Tefrethen's paper, where he applied the idea of the pseudospectrum to the Navier-Stokes equations in channel flows, or what's called wall-bounded shear flows. And the idea was that when people look at hydrodynamic stability problems and they look at the spectrum and they get results that don't conform with reality or simulations, they normally used to blame nonlinear interaction on this. They say, well, the linear theory is really not applicable because we are in a so-called strongly nonlinear regime. It turned out that that's not really what's going on. What's going on is that the linear dynamics still explains what's going on, except that the eigenvalues do not tell you the story. It's more robust quantities, so you have to think about either input-output norms or transfer functions or the pseudospectrum. And so this really tied in with robust control. I mean, that was a perfect match between that theory and robust control. They were doing A plus delta, but you could do much more structured uncertainties that are more appropriate for the fluid dynamics problems.
I'll play devil's advocate at this point. So just to clarify also to our audience, what is an infinite dimensional system? What do we mean by spatially invariant? And also clarify the fact, I don't know whether this is correct, but the first paper that I found in your records that deals with spatially invariant systems should have probably come out at a CDC, I believe, in 1997 in San Diego.
Yes.
The title of the paper is The Structure of Optimal Controllers of Spatially Invariant Distributed Parameter Systems. This is a single author paper that you put out. Of course, there will be a link in the description, and very much recommended also to our audience, because it seems like the beginning of a journey that seems to last to this day almost, I would say.
Yeah, I mean, well, I was fascinated with the question of when you have a spatially distributed system described by PDEs, say, and then you have the distributed control problem, which, to be more precise, is you have let's say you're looking at wave motion. So you have a field which behaves according to wave dynamics, the wave equation. But you also have a control input which is distributed in the sense that it acts at every location in space. So this would be an idealization of, say, the discrete version of that, if you will, would be, say, a network of oscillators. And every oscillator has a local control signal, which you can then build with a feedback controller based on measurements, say, from everywhere. It's a highly idealized problem, but these highly idealized problems are useful for understanding structural questions. So there was also work related to, in the robust control literature in the 80s and 90s, related to time invariant versus time varying compensation. And so there were these results by Bruce Francis and others, and then Jeff Shamma and Munzer Dahle wrote a paper with a general technique for showing that for essentially in any norm, a robust control problem with a linear time invariant plant, and then the question is, if you allow yourself to use time varying controllers, can you do better than having time invariant controllers? And they showed that the answer is no. In some sense, the optimal controller inherits the time invariance of the plant. So the idea is, okay, so now instead of looking at time invariance, let's look at symmetries in space. So you have a spatial system that has spatial symmetries. Does the optimal controller inherit those symmetries? The origin of that paper was to try to answer that question, and I used sort of a spatial version of time invariance, which is spatial invariance. Your space is infinite, and then you're invariant to shifts. So that's the kind of the simplest symmetry you can ask for in spatially distributed systems. And the answer is, again, the same, because essentially the proof technique is the same as what Shamma and Dahle did, but in space rather than in time. And people always asked me at the time, well, but this is a very idealized case because you always have boundaries in space and so on. And then my answer was, yeah, I understand that. But to answer structural questions, you need certain idealizations. I mean, think about time invariance. Most systems in reality are not time invariant, but the time invariant idealization is very useful.
And in fact, I think you actually write something about this in the conclusion of, this paper is actually the precursor of a paper that then appeared on the transactions on automatic control I believe in 2002, but I was reading that it was received in 1998. So the paper was published, but it actually won an Axel B award. So it was probably worth the effort of waiting the publishing time.
Well, that was primarily my fault. So then I teamed up with Fernando Paganini and Mondo Dale, and then we worked on this paper. And for 4 years, it kept going back and forth. We ended up having to add some material about the details of certain proofs because some of the reviewers were questioning those. But it took 4 years primarily because I'm a procrastinator. So it was partly my fault, and Fernando and Munzer were right on top of it. So yeah.
To be clear to our audience, the paper is Distributed Control of Spatially Invariant Systems. It's a joy to read. It's filled with intriguing side results and remarks. I strongly recommend it to the audience. It's a must for every control geek out there.
Thank you.
There's many points that I'd like to discuss about this paper. I don't know whether you want to start, give an overview, or whatever you prefer.
Maybe just quickly say, so let's think about, I'll give a very simple example. So if you think about consensus algorithms, which is something that are very well known these days, and you think about a consensus algorithm over a lattice, which is, say, 1 or 2 dimensional lattice. That basically is a form of diffusion. So if you run this algorithm, its dynamics are very similar to diffusion. It's basically the discretization of the diffusion equation on a lattice. And so the analogy here, maybe it's good to think about discrete space versus continuum space analogies, which I find to be very useful. So controlling the diffusion, distributed control of the diffusion equation, which is a PDE, is essentially the continuum version of the discrete space problem, which is, say, a consensus algorithm with additional controls as well, distributed controls. Mathematically, they are very similar. Phenomenologically, in terms of what you expect to see in both the open loop dynamics as well as the controller design, is also very similar. And so I've been advocating this view that you should think about distributed control on networks as the discrete space version of distributed control of PDEs. So you can make many analogies, like the wave equation corresponds to the swing equation, let's say, of AC power networks or vehicular formations. Diffusion equation corresponds to consensus in undirected graphs. The advection equation corresponds to consensus in directed graphs, for example, and so on and so forth. There's a whole taxonomy of these equivalences that you can show. So in that paper, what we did is looked at problems on lattices, which were discrete space, like Zn, or Rn, which would be PDEs, or problems on the circle, so that's PDEs with periodic boundary conditions, or problems on the discrete circle. And these are all different manifestations of a type of spatial Fourier transform that you can use to solve the problem. Now, using spatial Fourier transform is not terribly innovative because everybody knows how to do that. But what we discovered actually is the structural properties of the optimal controller. So we used an analytical extension technique. So for example, you look at the distributed controller for the diffusion equation PDE. So it's pretty straightforward to take over an infinite domain, you take a spatial Fourier transform and you can solve it in Fourier space. But you can go one step further and you can actually realize that the optimal feedbacks are convolution kernels, of course, but they have exponential decays, which means you get this property for free, which was kind of surprising, that the optimal controller is essentially localized. Even though you ask for the fully centralized controller, it turns out to have a degree of locality in the sense that you can show that these exponentially decaying convolution kernels are, in both the LQR and the estimation problem, your feedback kernels are exponentially decaying. And that rate of exponential decay depends on the plant parameters as well as the performance objective. So you can show very simple and intuitive results like the following. In a LQR type problem for the diffusion equation or most other equations, you can show more or less analytically that in a cheap control limit, so when your actuator authority is very good and very high, your convolution kernels become very localized, meaning you don't need information from far away in a network or in your spatial domain. While in the expensive control regime, the convolution kernels become much fatter, and it means that the optimal controller, because it doesn't have a lot of local authority, it can benefit from getting information from far away. So these, again, are the structural issues that I think these idealized problems give you. It's not so much to design the controller, it's just to understand the structure. So once you realize that you don't need information from far away, you can implement a controller designed by any other method, for example, and vice versa.
This is wonderful, actually. I'm glad that you brought up the example of I wonder, so diffusion, just to clarify, is the same as heat equation?
Yes.
Okay,
yeah.
Just because I'm not a PDE expert. So, and that was actually the example that struck me the most, because as you say, you do show that there is some sort of inherent locality property somehow of the optimal controller. And this is still so pertinent today, basically, as a question. So as a question of controller architecture, how to control a quote-unquote complex system, but ideally in a distributed fashion. This has been something that has been studied for long, and I think will be studied also for quite a few years. But of course, you didn't stop there. So this is just the inception of the journey, I would say, right?
May I make a comment on this? So,
of course.
So, Alberto, I tend to go off on lots of tangents, so you have to kind of rein me in at some point.
No, please do.
This brings up, the structural issues brings up a very important point that I'd like to emphasize, because I think maybe people forget that sometimes, especially today. So I find that optimal and robust control is most useful, and this has been kind of known in the robust control community in the 80s and the 90s. It's really most useful for understanding structural issues, not so much for actually designing and implementing a controller. People say, why are you so obsessed with optimality? Why don't we just design controllers that work? We know how to design controllers that work. We have a whole bag of tricks for doing that. And that's fair. But again, as was kind of well known in the robust control community, optimal and robust control design is actually most important for understanding limitations of performance. Is a plant hard to control or not? And then if it's hard to control, then because the best achievable performance is really bad, then you should go redesign the plant. That's really what it's used for, most useful for. Things like body integral limitations and the right half plane poles and zeros that give you these limitations, these are very useful design techniques. They inform how you can redesign the plant. So I was carrying that same idea into the spatially distributed control arena, which is, what should the structure of the optimal controller be? And once you know that structure, like, spatially invariant or, localized with a certain locality region, once you know these structural answers, then you can go and redesign your controllers in many other ways, using multi-agent system ideas or other ideas. But the idealized optimality problems are useful for answering structural questions.
It informs and design, basically, the design process of the plant.
Of the plant, not just the controller, right? And,
Amazing.
Nowadays people say, well, we can use reinforcement learning, we can use lots of data-driven and reinforcement learning or MPC, etc., which is great, right? But you have to have designed the plant already to make use of these techniques.
At this point in time, we are in 2002. I then see that there's many different directions that you take from this paper. Perhaps what piqued the most my interest is the work that you carried out with Mihailo Jovanovic. You've been doing incredible things with the Navier-Stokes equations, which again look like incredibly ugly beasts from outside for a non-expert, but you somehow have a different opinion, I guess.
Yes.
Or at least you bring up a point of view that allows us to simplify the analysis.
I mean, this is a fun story, and has many aspects, but I'll try to mention what I think maybe is more relevant today. So we started this work because I wanted an application for distributed control theory that we were developing. So I was looking at problems where large arrays of sensors and actuators are possible. And that's, you want to design controllers, distributed controllers for those. There was a joint project between UCLA and Caltech, mainly fluids and MEMS people. They were designing these arrays of magnetically actuated flaps and shear stress sensors for boundary layer control, as they were calling it. And I thought that was an intriguing problem. So I thought, okay, here's a large sensor actuator array. I can apply sort of just my distributed control ideas to it. But first, I need to understand the dynamics that I'm trying to control. And that's the Navier-Stokes equations. And then I looked into that literature. There's a bit of mythology about Navier-Stokes that is so complicated, and because its behavior is very rich. And then, you always ask the question is, what do you advise younger researchers to do?
Yes, I do.
And I think many times for me, it was finding that one paper that speaks to you, like all of a sudden clears up all the confusion that you've been seeing in all of the other papers in the literature, because that paper speaks to you. It explains it in terms you can understand. And that for me is, that's the paper I found by Nick Trefethen. It's a beautiful paper and it appeared in Science. It's called Hydrodynamic Stability Without Eigenvalues. And that's a fascinating story that I'd like to just spend maybe a couple of minutes to describe.
Definitely.
Because this is very relevant to control theory. So hydrodynamic stability is an old field that goes back to the 20s. And the idea is that fluid flow has a lot of instabilities, in the sense that you can think of laminar flow as an equilibrium point of the Navier-Stokes equation. It's an equilibrium solution, if you will. And then as you change a parameter, namely the Reynolds number, at some point that equilibrium solution becomes unstable. And so the flow with tiny perturbations will evolve away from that equilibrium. And people think of that as sort of the first step on a route that leads to turbulence. So the first step is always analyzing an instability. So you take the Navier-Stokes equations, you linearize them around laminar flow. This is a process we all know how to do, right? You take a dynamical system with an equilibrium, you linearize around that equilibrium, you check the eigenvalues of the Jacobian, right? So the hydrodynamic stability is basically a PDE version of that. You take a laminar flow and then you linearize it, you get a linear PDE, you check the eigenvalue problem for that PDE. Mm-hmm. In the 20s and 30s and 40s, they were doing it with a lot of clever asymptotic techniques, kind of an art that seems to have been sort of forgotten now. And then later on, it's mostly done numerically. But this is a very successful theory. It explains many phenomena, from fluid flow in the lab to atmospheric phenomena to even stellar phenomena. So there are certain hydrodynamic instability problems in star formations and galaxy formations that have been studied. To that, the book by Chandrasekaran, famous one, addresses some of these problems. However, this theory did not give the right answers for one very important regime, which is boundary layer shear flow regimes, like flow in pipes, flow around streamlined surfaces, which is very important technologically, right?
Yes.
And it always gave the wrong answers. In fact, funny enough, this was Heisenberg's PhD thesis. His advisor, Sommerfeld, was a famous fluid dynamicist, and his PhD thesis was on hydrodynamic stability. He was addressing this difficult problem of boundary layer instability, not very successfully. So he moved on to quantum mechanics, which was a much easier problem, apparently.
It was too difficult for Heisenberg as well. Wow.
Yes. So in the 30s, Tolmain and Schlichten came up with sort of asymptotic analysis, sort of these difficult asymptotic expansions, match asymptotic expansions, that gave answers to this particular problem in channel flow. They predicted an instability that would occur at Reynolds number roughly 5,700. And for about 10 years, nobody could repeat it, could find it in experiments. Until at the very end of the 40s, there was a very careful experiment done in an extremely clean wind tunnel. And there was, in fact, the instability had to be triggered with what's called a vibrating ribbon technique. And then finally, those so-called Tolmain-Schlichting waves, which when you linearize Navier-Stokes in that geometry, you see that there's above Reynolds number 5700, there's an eigenvalue that creeps into the right half plane, which will cause an instability. That's called the Tolmain-Schlichting mode. And then that experiment, after efforts of 10 years, finally showed that. And then it was considered a big discovery because we finally uncovered the origins of turbulence in boundary layers. The problem is that this is a very, very weak instability. You only see it in extremely careful experiments, very clean experiments. And then what happens in any normal experiment is that you get transition to turbulence from a different route, and which is called normally the bypass transition, because it bypasses this theoretically predicted instability. And the idea that was common is that in this particular geometry, nonlinear effects are really important. So the linear theory fails because you quickly move to the nonlinear regime. And then much later on, in the 80s and 90s, the work of Trefethen and in particular Brian Farrell and Petrus Ioannou at Harvard, not Petrus Ioannou from controls, and the geophysical fluid dynamics
I did
guy.
make the connection, actually.
Yeah. They actually showed basically that the problem isn't that the linear problem doesn't predict instability, is that you're looking at the linear problem incorrectly. The linear problem, in this case, is extremely fragile in terms of eigenvalues. So you calculate the eigenvalues in Navier-Stokes, you have to calculate them very carefully to get them, but you make any tiny perturbation in the system dynamics, and those domain shifting waves disappear, right? You get something else that goes into the right half plane. So that was what Trefethen was calling the pseudospectrum analysis. And ironically, this story is full of ironies, because calculating this is called the Orr-Sommerfeld problem for channel flows. Calculating those eigenvalues numerically was a notoriously difficult numerical problem. So in 1971, Orszag wrote a paper on using what's called Chebyshev collocation pseudospectral methods for calculating the eigenvalues. And he was able to calculate the eigenvalues to several significant digits. And this became a benchmark problem for numerical eigenvalue routines, because this problem is so sensitive. So when you develop a new routine for the eigenvalue problem, you test it on the Orr-Sommerfeld problem against Orzak's table to see how many significant digits were you able to compute those. And the reason is that this is a very, very sensitive, basically, system. With small perturbations, the eigenvalues move. And from a robust control point of view, the perspective is those eigenvalues are not important. Calculating them to 8 significant figures is not important because they're not robust anyway. You should instead calculate robust quantities. So when we looked at this problem and we calculated system norms instead of the eigenvalues of the A matrix, it turned out you could do it with much, much coarser discretizations. You don't have to be very careful with the numerics because system norms are robust quantities. So, I can go on about this, but that's...
Please, it's amazing. Yeah. So did you actually get in touch with Nick Trefethen afterwards? Or?
I did. And I explained to him, the pseudospectral analysis is very much like robust control. And he was excited to learn that, yeah.
Very cool. And so this is the origin as to why you started looking at the Navier-Stokes equations?
Right. Yeah, and so when Mihailo Jovanovic started working on these problems when he was doing his PhD, while doing two other problems as well for his PhD. His PhD is really a massive achievement. And so Mihailo has really carried this to show in various flow regimes, also in the supersonic regime, that analysis turns out to be very informative. He also looked at, so I'll connect this with vibrational control, if you will, because that's another fascinating story. The boundary layer turbulence is very important for what's called skin friction drag problem. So on most airliners, skin friction drag is responsible for somewhere between 20 to 25% of the total drag on an airliner. And then about half of that is due to the fact that the boundary layer is turbulent. In fact, most of the noise you hear in an airplane is not so much engine noise, but it's actually the noise of that boundary layer around the skin, which you kind of sort of acoustically propagates into inside the airplane. And it's much worse in the back than in the front, because that's where the boundary layer is thickest. It's more developed towards the back. So if you want to avoid that noise, you should sit in the front, not in the back. So on ships, big cargo ships in the ocean, skin friction drag is really big, right? That's responsible for a lot of your fuel consumption. So it's a technologically important problem. If you could laminarize the flow, at least you could reduce that skin friction drag substantially. That's different from form drag, which is the drag on blunt objects. But most vessels, ocean liners and airplanes are designed to reduce form drag as much as possible. But then you have to live with that skin friction drag, which comes mostly from the turbulent boundary layer. Now, there are fascinating examples in nature which seem to somehow have solved this problem to a certain extent. One of them is shark skin. So shark skin, especially the big sharks, they have grooves on their skin, and the grooves are almost like record grooves, so like about 1 millimeter in spacing, and they're in the direction of the flow. And those are called driblets in the fluid dynamics literature. And they're known to reduce this turbulent skin friction drag, somehow reduce the turbulent energy production. People have tried to repeat them in the lab with mixed success. So you can build these driblet structures and test them in water tunnels and see what drag effects there are. Dolphins have a completely different mechanism, but it seems to also be effective at reducing this turbulent energy production. So dolphins have a very compliant skin. It's so rubbery or spongy. And it's believed that the skin, there's a sort of a fluid structure interaction where the skin essentially interacts with the flow structures to reduce turbulent energy production. And the proof for this is that dolphins have been observed to swim at speeds that when you compute their muscle mass and the mechanical power they can produce, they must be somewhat partially laminarizing the boundary layer around them. Otherwise, they wouldn't be able to swim at those speeds.
Amazing.
So this is a form of, if you will, passive control, right? There isn't really feedback, but the structures are designed to interact with the dynamics of the boundary layer so as to change the dynamical behavior. So the riblets problem has been really vexing for a long time. And then Mihailo has found actually a very interesting interpretation of this. So the riblets, if you think about them, they are really corrugated structures, and the corrugation is kind of perpendicular to the flow direction. So we always thought this may be a PDE version of vibrational control, because it doesn't require feedback. What it does is it's changing the properties of the PDE in a periodic manner, spatially periodic now, rather than temporally periodic. And so maybe it's a manifestation of a spatial version of vibrational control. And Mihailo has recent work actually in the past 2 years where he actually shows that that is indeed the case. And you can predict the amount of turbulent energy production based on the spacing of the riblets as well as the amplitude. So in a way, this is similar to in vibrational control when you're trying to control the Kapitsa pendulum, where your amplitude and frequency of excitation has to be chosen just right so you can stabilize in what people call open loop, right? Meaning without actually sensor feedback. And I feel that in the area of flow control, this probably has more of a future because you don't need to have an array of sensors. You're really changing the structures so as to change the dynamics in a more favorable regime. Yeah, so vibrational control has a spatial version of it as well.
So maybe in the future we will see airplanes of different materials outside based on what you're saying that implement this form of passive control.
Yeah, these riblets have actually been tried on ship hulls because there the skin friction drag reduction problem is even more important. But again, you have to design them. You can't just design them by trial and error. The problem is too complicated. You have to design them so that their spacing and amplitude is right. And what's interesting about this is that the spacing and amplitude is Reynolds number dependent, which means if you think about a ship hull, it varies along the ship hull. So you can imagine kind of a skin design whose properties vary as you move backwards towards the backside of the ship. So it's a complicated problem that still needs to be resolved.
Actually, here I'll try to play again devil's advocate for the audience to clarify. First of all, what is the Reynolds number for those who haven't heard it?
You could just think of it as flow velocity. Yeah, it depends on viscosity and length scales, but you can just think of it as flow velocity. Fluids, especially in 3D, they don't want to go in a straight line. They want to swirl, they want to form vortices and tumble. And so fluids are very quickly can become unstable. And the equilibrium flow very quickly becomes unstable. And this is what I was saying about plasmas earlier. So if in addition to that, you add an electrically charged fluid that could be in a magnetic field, then it even wants to be even more unstable.
The other question that I had related to this topic, because we started initially thinking about what happens as we essentially move towards turbulence, whether this can be thought of as some sort of form of bifurcation almost that happens at some point whereby we see a qualitative change in the behavior of our system.
Actually, yes, I should mention this. Traditionally, the route to transition to turbulence has been thought of as a bifurcation cascade. And in fact, you can do experiments and you could do very, very beautiful mathematics to show that you get an instability and then these structures grow. And then you linearize your Navier-Stokes around these new structures and you discover a secondary instability, which then also grows, and you can keep doing that. And then very quickly you get a bifurcation cascade, and then very quickly the flow structures that arise become very complex looking. That's one route to transition to turbulence, but it is not the only route. So the analysis that we did shows that especially at high Reynolds numbers, high velocities, the flow becomes very fragile, very sensitive to it. So if you have a little bit of thermal fluctuations or a little bit of surface roughness, that's enough to make the flow look very turbulent. In fact, one way to think about it, so think about a flow past a very smooth surface, except it has maybe microscopic roughness, but it's running at a very high, let's say even supersonic speed. What the flow dynamics, you can even think about the linearized dynamics. They act like an amplifier. So the small wall roughness gets amplified many, many orders of magnitude into the flow. So the flow is a big amplifier in some sense of the ambient uncertainty.
Okay.
And if you do the input-output analysis, this is very much like what we do in systems theory. Instead, now you do spatiotemporal input-output analysis. And you look at the power spectral densities that you expect to be in the output. They turned out to be remarkably similar to what you see in experiments and CFD.
That is wonderful. One very quick question. Why do we have to consider noise in these equations? So because you speak about power densities, so that implies that we are in a stochastic setting.
Yes.
Why do we have to use that?
Well, because again, the system you can think of it as a closed system, which is how traditionally dynamical systems people think about it, right? But if you think of it as a closed system, you're basically saying there are no other physical effects in the world except the Navier-Stokes equation. But in reality, your boundary conditions are not clean. In many flow problems, the flow that's coming in has what's called free stream disturbances. So it comes in with a little bit of fluctuations. And then what you can show in even the linearized problem is that if you take the Navier-Stokes equations and you add disturbance inputs, which are body forces, you can show that the input-output norms scale with the Reynolds, like with the cube of the Reynolds numbers in certain cases, or depending on which norm you use, but they scale unboundedly with the Reynolds number. So at high Reynolds numbers, the system becomes an amplifier to any small amount of ambient noise. And so a noiseless analysis where you consider the system to be closed is not going to reflect reality.
It's amazing. So, okay, and that's the reason why you should really think about gains rather than eigenvalues, as you were saying before.
Yes, and with Mihaly, when we published this paper in Journal of Fluid Mechanics, we called it input-output analysis, which is a term the fluids people don't understand. So, but it's coming from controls, it's a very natural thing to do.
Absolutely.
You can if you indulge me for 1 minute, I'm gonna state a theorem which will explain all of this. So we think about underdamped systems that have eigenvalues, poles close to the imaginary axis. We think about them in terms of their frequency response, and we think that the frequency response has peaks, resonances, close to where the underdamped poles are. It's a very intuitive, we've seen it in vibrations analysis, we see it in many problems. However, so you could think of the poles or the eigenvalues as an internal description of the system, because if you have no excitation, the system the response will be made up of these modes. And we think about the frequency response as an input-output property. It's an external description. And now you can ask the question, what is the fundamental relation between the internal modes, which are the eigenvalues, and the shape of the frequency response, where the resonances occur? And you can easily prove a result that says there is no possible, in general, there can be no relation. So give me any frequency response, say in H2, and then give me any prescribed locations in the left half plane. I can fit that frequency response to arbitrary precision in the H2 norm with a system whose poles are where you wanted them to be, anywhere you chose ahead of time. But you must allow me high dimensions, multiplicity of poles. And so in principle, there need not be any relation between the internal modes and the input-output picture. But you need high dimensions for this to happen. And this is very unusual. We hardly ever see this, but this is exactly what happens in the shear flow turbulence problem. The input-output resonances are somewhere very far away from where the poles that are very close to the imaginary axis are. So that's sort of another way of viewing this particular, apparent mystery.
It's somewhat surprising if you think about it with a closed loop mindset, but if you think about it from a controlled perspective, so in this case from an input-output perspective, it's not surprising. And the message I would summarize it as the I/O input-output behavior is not always predictable from the modal behavior, so from the shape of the modes.
Yes,
basically.
exactly.
Super interesting.
Yeah, and this has to do with, for example, so the way applied mathematicians and others, you can, in MIMO systems, let's say, B and C matrices are identity. For this to happen, you need the A matrix to be what's called non-normal, meaning its eigenvectors are not orthogonal. So, and in some areas, this whole sort of phenomenology goes by the name of non-normal growth.
In some other communities, this is something that is quite popular as well. And also it relates also to what we were discussing before at the beginning with the example of the shift operator, right?
Yes, exactly.
So at this stage, there's many directions where we could go. One that I found particularly interesting, again, in order to analyze, if you want, this tension between discrete and continuous, lattices versus continuous media, and the concept of control architecture, locality and localization of controllers. One paper that definitely fits nicely into this picture is this paper on coherence in large-scale networks. I find that another gem that everybody in the controls systems realm should read at some point of their life. I'll let you explain what that is all about.
I'd love to. So this is another problem which has connections with problems in physics, but a completely different area. And that's connections with condensed matter physics, or sort of maybe we call it solid state physics. And the connection is not as strange as it might seem. In multi-agent systems or distributed control, we're talking about the interaction of a large number of subunits. And in condensed matter physics, they study the interaction of a large number of units, but the units are atoms and molecules and so on. And for us, the units could be vehicular platoons or generators in a power grid, etc. So it is not that surprising that phenomenology is common in both areas, and maybe even some of the mathematical tools may be useful. So this problem actually, our interest in this problem goes back to Mihailo Jovanovic. Again, in his thesis, aside from the Navier-Stokes, he also worked on vehicular platoons problem. Because again, we had this theory of distributed control, and we were thinking, let's find a nice application where we can sort of see how this works out in reality. So we looked at the problem of platoons. So this is the problem of vehicular formations of a single string of vehicles on a freeway that's automatically controlled. And the idea was that you can increase the throughput on freeways rather than build new lanes if you could have very tight control. So at one point I was giving this talk, and a European control researcher in the audience said to me, where I was describing where you want to make these cars move on a freeway with very tight spacing, 1 or 2 meters at highway speeds, with devices that ranging devices that measure their positions and velocities, etc. And then he said to me, "Well, you're basically creating a train, right?" So yeah, it's creating a virtual train. That's true, but Americans like to be in their cars on the freeway, not in train cars. So, but anyway, so we looked at idealized versions of this problem, and then we tried to make the platoons larger and larger, and we started seeing sort of strange behavior in the simulations. And so Mihailo wrote this paper called "The Imposedness of Certain Vehicular Formation Problems," meaning that as the size gets bigger, even when you do the optimal LQR problem, you still get basically bad behavior. And so if you simulate this formation subject to any sort of disturbances, with stochastic disturbances, it turns out it's not traveling down the freeway like a virtual train. It's wobbling like an accordion, right? And it's not very rigid it's not a crystal lattice. It's basically acting like a fluid instead. And so we're wondering, whether this is fundamental or we just didn't know how to design good control laws for this distributed control problem. And then I was discussing this with a physicist, a friend of mine, Partha Mitra, who said to me, "Oh, yeah, but this is just like, this is because your problem is 1D, and this is like the harmonic solids problem, where you can't have a long-range order with only short-range interactions." And then so I had to understand what that means. I don't know if you talk much to physicists, but often, physicists are very bright people, but sometimes they think that engineers cannot teach them something that they don't already know. But I was skeptical because, feedback control systems are really much richer than atomic interactions, because you can have memory in the controller, et cetera, which you don't really have in molecular or crystal lattices. So we studied this problem and then showed that under some conditions, that this problem is really fundamentally difficult, in the sense that if you increase the size of the platoon and subject to stochastic disturbances, this wobbling motion, which you can quantify by a variance, you can show that variance grows either as n or n cubed, depending on what you allow for the feedback control laws. And so you cannot really have large coherent formations with only local feedback rules. Now, the way people get around this in the platoons literature is there's an underlying assumption that every vehicle knows its distance to a leader, and the leader kind of carries this sort of absolute frame of reference. And if you have that, then this problem disappears. This lack of coherence problem disappears. Now, people can debate whether that measurement is feasible to get an accurate measurement of your distance to the leader at the time scales required for doing this real-time control. People propose a communication structure, inertial navigation on each vehicle, and you can potentially transmit that piece of information to each controller. That's another discussion. But the fascinating thing about this is that if you make your formation 2D or 3D, then the problem is very different. So, for example, in 3D, you can have a very large formation that looks like a rigid crystal lattice, just because there's enough connectivity in a 3D lattice to enable local interactions to produce sort of this globally coherent phenomenon. The way the physicists think about it, this is the harmonic solids problem, which is interesting, is they look at crystal lattices as a bunch of masses and springs. So this is a classical model for crystal lattices. And then the question about long-range order is the following. In a solid crystal lattice, the position of an atom here is correlated with the position of an atom billions of sites away because it's a crystal lattice. So how do you get this correlation over very large distances with only nearest neighbor interaction? And so what you show is that in 1D, this is impossible. That's a harmonic solids problem. 2D, the 2D situation is more complex, but in 3D and higher, it is possible. So you can have, the correlations can go to infinite distances even though you only have local interactions. You can ask the same question on general graphs, much harder to answer on general graphs. But the lattices are really a way of thinking about connectivity. So the dimension of a lattice, whether it's 3D or 2D or 1D, is really a proxy for connectivity. When you have sufficient connectivity, then local interaction rules can lead to some kind of global order. But with loose connectivity, you don't. And connectivity can be quantified in many different ways. And you can easily show that node degree, the number of neighbors of each node, is not a good measure of connectivity. Because you can have a one-dimensional lattice where you talk to not just your neighbors, but the second neighbors. And this has node degree 4. While a 2D mesh has node degree 4, but both scale very differently with the size of the formation. The variance in one case scales as n, and then the other case scales as log of n. So very different. So node degree really is not the correct notion of connectivity in these kind of network problems where you're thinking about the emergence of a coherent structure.
And that's actually if you want, the takeaway that I got from, aside from the whole paper, as I said, really being fantastic to read, it's this table that you have on page 2 or 3, where you have a summary of what happens in every dimension. And it's somewhat surprising that in dimension 1, you do have a fundamental problem.
Yes.
With localized feedback, basically. It's this tension between absolute feedback, as you were saying, so having this point of reference to a leader versus just pairwise interactions between either each of these particles or cars as we think about them.
Yes.
And do you have an intuition behind why this happens in one dimension? So why it cannot be, why do we have this fundamental limitation?
So the intuition might be, again, to think about connectivity. So the situation here is that every node is subject to a stochastic disturbance. So the disturbances are coming in at every node. And then the links between the nodes are really the regulating feedback loops. They're trying to minimize the effect of the disturbances. And the disturbances are coming everywhere, and all of these loops are trying to fix the problem by providing sort of pairwise interactions. In 1D, the connections are not enough to overcome the disturbances. In 3D, you have enough connectivity that as disturbances are coming in, these feedback loops are trying to correct for that, and there's sufficient sufficient pattern of connectivity that the feedback laws, the interaction feedback laws actually win in the end. So I think of it as the ability to have enough connectivity so that somehow your local feedback rules produce some kind of a global order. While in 1D, it's just not enough connectivity to overcome that.
Amazing. Really fantastic. So actually, in this interview that I also mentioned before on the Control Systems magazine, People in Control, you also mentioned that in either case, both the discrete and the continuous, which we have visited in this discussion, the notion of controller architecture is one of the most important research questions. I was wondering what's your understanding now of this question today, basically?
I'll give an example, which I think this is still an open problem. So when we, which is sort of the realization theory for distributed controllers. So if you think about realization as we understand it for lumped systems, we think about, minimal realizations are controllable, observable. That kind of answers the question of what is the dimension of the realization. And then you can think about various types of model reduction, like balance truncation or other kinds of balancing. And more or less the question of complexity of a controller implementation is related to the order of the controller. which is the dimension of the realization. In distributed control, it's a very different issue. So at each site, there is a controller, which is taking in measurements from other places. But that at each site, the controller has a dimension. You can choose that dimension. And then when you think about the distributed controller as a whole, what is the right notion of controller complexity? Is it the total dimension? Is it, the dimension at each state? And the controller complexity is a much richer question now because, as has been shown in many results, partial results, and so people have intuition about this, that if you can enlarge the order of the controller at a particular site, you can do with less sensor measurements from far away, in the sense that basically the controller has a built-in estimator to try to estimate the state of the network far away. So there seems to be a trade-off between the local dimension of the controller versus the communication requirements of what the controller should be sensing. So we don't really know how to quantify that trade-off, as far as I know. Maybe some other people know this, but I think that's a fundamental problem in distributed realizations. People like Nicola Elia or Anders Ranser have addressed this question, but I still think this is kind of an open problem. It has to do with controller architecture and what is the right notion of controller complexity in the distributed sense, in the distributed setting.
And this is also related, by the way, to something that we haven't mentioned in this Coherence in Large-Scale Networks paper, which, by the way, got you another Axel V Award, one of the most prestigious awards in controls. The critical dimension needed for global coherence is this rule 2n+1. I don't think we actually mentioned this. Maybe I should let it explain to you. So the role of node dynamics.
Oh, yes. It's great you mentioned that because that is a mistake. That is incorrect. Yes, this was stated in the conclusions section.
Okay.
But Emma Tegling at Lund University has recently shown that that's incorrect. So it was kind of a careless comment that I made just based on the intuition, which turns out that the intuition is wrong. So the N was the number of integrators in the open loop at each site. In vehicular platoon's case, it's a double integrator. Each vehicle is a double integrator. So 2n+1 was 3. So in dimension 3, you get coherence. And so I kind of conjectured that when you have a chain of integrators, the point is that the integrators kind of slow you down, right? So your performance objective is at the output of the last integrator, and your disturbances are coming in at the input. And you're measuring. And so, when you have a lot of integrators, the disturbance has time to wreak havoc into the system before you can actually see its effect in the outputs and try to correct it with feedback. So what Emma has shown actually is that if you have more than 2 integrators, it is impossible to design a modular feedback law. So there's a feedback law that you apply to every new agent that comes into the system. And so you can grow the network with the same set of feedback laws. For when you have 3 or more integrators at each node, eventually there will be an N where you will go unstable.
Wow. Okay.
So you have to redesign the feedback laws as the network is growing.
Incredible.
So that statement is actually incorrect. I'm sorry to admit that, but yes. But that was not part of the results of the paper. This was a sort of a statement in the conclusion section.
In the final section, yeah.
Yeah, where I let my intuition... intuition doesn't always work very well. So...
Well, you've shown it also with the input-output analysis of turbulent flows.
If I just may say something about this.
Sure.
I think an interesting thing about this table is that it matters which quantities you're able to feed back in an absolute frame versus a relative frame. So in the vehicular formations, it is easy to use a feedback law based on your absolute velocity because you have a speedometer in the car. So that measurement, that feedback law, you can do according to an absolute frame, even though with position measurements, it has to be done in a relative frame. So that's your critical dimension at 3. But if you don't have a speedometer, so imagine that gives you your position relative to an absolute frame. So think about a flying object, with only inertial nagnification, which may not have very accurate absolute position measurements. then the critical dimension becomes 6, not 3. And in 1D, the growth of the variance is n cubed rather than n. So it's a much worse situation. So again, these are architectural issues. So what is it that you have available, and is it available in an absolute frame or a relative frame?
Yeah, it's incredible. Somehow I don't have an intuition for all of these quantities, even though it's absolutely fascinating that, again, in this table you measure this tension between absolute position, absolute velocity, relative position, absolute velocity, relative position, and relative velocity, and they all lead to somewhat, well, in some cases, surprising results, at least surprising to me.
Yeah. Again, let me so I showed this result to a physicist, and then when I showed him that in this particular scenario, when you don't have velocity feedback, the critical dimension is 6. He said, surely this is wrong. This cannot possibly be true, because they have what they call universal classes, universality classes, and he'd never seen a dimension 6 result. So then eventually I convinced him that it was correct. But his first impression was, this can't possibly be true. But engineering problems tend to be sometimes different from physics problems. And this was one instance where that's true.
Did you ever also make the connection to, let's say, coherence of formations that appear in nature in relation to these dimensionalities issues? I'm thinking about, flocks of birds or fish school or...
So, I mean, if you think only intuitively, I haven't studied this. For example, Naomi Leonard studies these starling flocks. And in fact, for quantifying the order that you see in starling flock swarms, they used an H2-like norm, very similar to the one we used in our coherence paper. And so, but they actually used real data for that. But if you think intuitively about a flock of geese, right, they're traveling usually in this V formation. Even though they're flying in 3D, this is really a string. It's a one-dimensional string. While if you think about a school of fish, usually they are interacting not just with sight, but they actually feel hydrodynamic forces from their neighbors. They're close enough that, the motion of the neighbor will induce pressure variations onto the skin of another neighbor, which then can provide sensor measurements, which they can react to. So a school of fish, you could think of as a three-dimensional lattice, if you will, as an idealization. And our coherence result shows that can be much more coherent than a 1D string, which may explain why they seem to swim in very, very tight patterns that seem very coherent.
Maybe this is a good time to shift gears.
Okay.
I was wondering, how did you end up studying resistive losses in power networks? Oh. What does that have to do with everything that we talked about until now?
Okay. So, with Mihailo, we looked at the platoons problem, and then the equations at each cite their second order. And then you look at the swing equations of power networks, and they look exactly the same, almost the same. Except now it's generator angle and generating angular frequency that are state variables rather than position and velocity. And so we thought, let's think about analyzing power systems in the same way. And then a problem that, and so I ended up doing this with Denise Game and Emma Tengling, who we did this analysis, and we thought, let's think about the coherence of a power network, the coherence of phases and frequencies in a power network. And we were thinking about it in terms of the same thing as the coherence of a formation. But then we started thinking, let's think about a different problem, because the thing about the power system is that it's self-regulating, but it is self-regulating by exchanging reactive power back and forth between generators, which tug on each other so that they can maintain the phase relationships and the same frequency. So the signaling mechanism in a power network, the control mechanism, is really reactive power sloshing back and forth between generators. That's different from the real power that gets dissipated at buses, that gets consumed. This is just the regulatory power, if you will, back and forth. And we thought, that has a cost, because there's some resistances in the lines. They're very small, but some resistance. So let's try to quantify that. So we did the calculation, was easy to do for idealized cases. And then we had a surprising result, which was that the amount of power lost in the lines due to only the reactive power slushing back and forth. So you can call that the cost of regulation with this mechanism, grows with the number of generators, assuming all equal generators, which is a very idealized case, and does not depend on network topology. So this was completely surprising to us because we thought, the previous results depended on network topology. 1D was much worse than 2D, etc. But in this case, it didn't depend on network topology at all, the total resistive losses. And the explanation, intuitive explanation that you can come up after you scratch your head is that a loosely connected network, like a ring, has larger phase fluctuations. So here I'm not talking about when phases go unstable, and I'm talking about a situation where the network is operating in the stable regime. It's just wobbling and fluctuating a little bit. And so in a loosely connected network, the phase fluctuations will induce power transmission back and forth for regulation, and then you get some resistive losses. But the phase fluctuations are big because it's a loosely connected network, relatively big. And so even though there's a small number of links, you have larger amounts of power sloshing back and forth. In a tightly connected network, the phase fluctuations are very coherent. There's very, very tiny phase fluctuations, but there's so many links and you're exchanging power that in the net, it's the same as a loosely connected network in terms of losses. But what it depends on is the number of generators. So our conclusion was it's something that maybe people should pay attention to, that in a future highly distributed generation power network, because you are using reactive power slushing back and forth as a regulation mechanism, the costs may become prohibitively high for such a network. If you have thousands of generators, it might not be a problem. But if you have billions or millions of generators, if everybody has solar rooftop and then plugging into the network with inverters, that may become an issue. It's not clear. And then when I gave this talk, a couple of people told me that, for example, there have been suggestions a long time ago, even in the 50s, of sending a high-frequency communication signals along transmission lines for phase information so that the local controllers at the generators can use that communication signal for regulation rather than sending reactive power back and forth. And nowadays, people argue potentially for using GPS clocks in inverters for phase synchronization as a global signal, as opposed to using, reactive power sloshing back and forth. So we came up with a name for it to try to alert people. I called it the price of synchrony. All right. So it's not the price of synchrony, it's the price of using reactive power to achieve synchrony.
And this is actually a part of the title of a paper that appeared on Transactions on Control of Network Systems in 2015, The Price of Synchrony, Evaluating the Resistive Losses in Synchronizing Power Networks. Of course, there will be a link in the description later. So actually, you anticipated one question that I would have had. So if the losses scale with the network size, this seems to be a good case for building a communication layer on top of the electrical distribution system. Am I missing something?
I mean, that's one argument. Yeah, it definitely enforces that argument. Now, I'm not a power systems person, so building a communications layer probably has other issues. I mean, the current system is very robust, right? Because you are actually using reactive power as a signaling mechanism. So you don't have to send any other signals to have regulation. If you have a communications layer, then you become vulnerable to communications blackouts, sabotage, etc., etc. So there are many other issues.
I have, again, lots of questions, but they are perhaps not necessarily related to spatially invariant systems or everything that we talked about until now. One of these questions is related to this beautiful paper that you wrote on Cochlear Instabilities. I learned so much from this paper. I mean, about how amazing is the cochlea in general as a device, if we think about it from an engineering perspective. So the title of this paper is called Stochastic Models for Cochlear Instabilities, if I'm correct.
Yes.
with Maurice Philo. I'll let you say what is a cochlea and why is it interesting.
Yeah, so this is the work of Maurice Philo, my former student, who's now at ETH. Maurice works on a theoretical problem of looking at systems with a multiplicative noise, where you can think of the parameters of the system themselves as being stochastic in time, and developed a very nice, beautiful framework for stochastic stability, very much like the robust control conditions for robust stability with structured uncertainties, except in this case, the uncertainties are stochastic and time varying. And you get there's a very nice theory for characterizing, and very computational, by the way, for characterizing not just when things go unstable, but when they do go unstable, what do the responses of the system, the growing structures, look like? And that theory was particularly suited for spatially distributed systems. It was motivated by problems in fluid dynamics. And then Maurice had worked on the cochlea before actually being a student with me. So he knew a lot about the cochlea, and he knew a lot about the research in the cochlea. So the cochlea is an amazing device. It sits in your inner ear. It's a helical, it's a loop, but if you unroll it, it's about 3 to 4 centimeters long, and it's an array of tuned resonators in a fluid sac. So these tuned resonators are various membranes connected by hair cells, but each resonator is tuned to a particular frequency. And then when the sound signal comes in, the vibrations are transmitted inside the cochlea. And then depending on the frequency of the input vibrations, various parts of the cochlea will oscillate. And then the nerve cells will pick up the oscillation at that particular location. So if you really think about it, it is a mechanical spectrum analyzer. Mechanically, it vibrates, and at various positions in the array, it vibrates according to the temporal frequency. So it converts the input temporal signal to a spatial vibrations that are then picked up by neurons that then get sent to the brain. Now, there are two aspects of the cochlea. One is this mechanical spectrum analyzer aspect, but there's another very important feature. It has an adaptive gain mechanism. The human hearing has an amazing range, 120 decibels. So when you're in a very, very quiet room, there is an adaptive gain mechanism that turns up the gain. In a way, it does it physically, or it's believed that your oscillator that is tuned, there are specialized hair cells that provide effectively negative damping within membranes that vibrate, which makes them more susceptible to an external excitation. So that's the adaptive gain mechanism. It sort of plays around with what is effectively a negative damping. And when you're in a very loud place, that gain is turned down, and then so you can then, your oscillations are not damaging in the cochlea.
It's amazing.
So this is similar to the iris of your eye for changing the amount of light coming in. But here, this is done actually in a location-specific manner. So there are problems that occur in the cochlea, and some are natural and some are annoying, where the cochlea will spontaneously oscillate. So here's something fascinating that I discovered from Maurice. This is that when in about 1/4 of the population, you can put a microphone inside their ear and you'll pick up a signal. The cochlea has spontaneously vibrated. Those vibrations are transmitted to the eardrum, and the eardrum is acting like a speaker.
Wow.
And so you can pick that up in about 1/4 of the population. Your brain is used to this, and it has tuned it out. So you never hear it. You're not aware of it.
Amazing.
Yes. In fact, this is how they test whether babies have healthy hearing, because newborn babies have this phenomenon all the time. So they'll put a microphone. If they see a signal, healthy hearing.
Wow.
Right? And as we grow older, kind of this mechanism seems to be sort of, tamped down, and then only 1/4 of the population has it. There's another phenomenon which is classified as a condition, which is tinnitus, where people actually hear the buzz, and it becomes very annoying and sometimes really debilitating. Okay, so there's disagreement in the literature about the root causes of these phenomena, but we thought, okay, we have this theory. we have a cochlear model that Maurice was, developed based on his knowledge of the literature. Let's apply the technique and study the stability of this adaptive gain mechanism, because you really have kind of an automatic gain control. And so you can imagine that you're kind of always operating near the edge of maximum sensitivity. You can imagine, if you have a controls background, that if there are certain uncertainties, this thing can go unstable.
Yeah.
It's a mechanism where the amplifier gain is too high and you go into an unstable regime. And we thought maybe that's the explanation for the spontaneous vibrations in the cochlea. They are an instability. So we used that theory and we did calculations, or Maurice did calculations for the stability margins. And so this theory is stochastic. So what it says is you have a certain parameter. This is the adaptive gain mechanism. And we assume that this parameter has slight variations. And we wanted to calculate how much variations, stochastic variation in that parameter do you need? What's the variance? So that you hit the limit of mean squared instability in this case. So it turns out that the system is so sensitive that a variance of about 4 orders of magnitude smaller than the mean, than the nominal mean in that parameter, will cause you to go unstable in terms of mean squared stability.
Wow, how can that be?
Well, because this adaptive gain mechanism is operating always at the edge of instability.
Wow.
To give you that high dynamic range that you appreciate. And it is known also in the literature that the tinnitus, for example, depends very much on your physiological state, if you're dehydrated or not. So it does depend on physical parameters. That's why we study that uncertainty. And then we also went one step further and then looked at the structures that evolve when you have this instability. So your vibrations will occur because this is a stochastic system. The vibrations will look stochastic, but they will have a certain power spectral or a spatial spectral shape, which we computed. And it turned out to be very close to where the frequency range that is most susceptible. I should backtrack a little bit. This adaptive gain mechanism is not at all frequencies. It seems to be more prominent in a particular mid-range, which is, I think, what is most important for hearing. And then when we calculated the structures that grow, they turned out to be structures in that frequency, the location corresponding to that frequency range. So that's another sort of manifestation that maybe it's the adaptive gain mechanism that causes the spontaneous oscillations.
So you may try to explain it as that mechanism gone wrong for those who experience tinnitus.
Yes. Yeah. I mean, that's the conjecture that you would make if you look at this analysis.
Any idea about how to fix it? Like also as a control theorist?
Oh, yeah. Yeah. So here are 2 ideas. So this is not something we have done yet, but these are sort of potential areas for research. Again, there's another irony here. One treatment for tinnitus. Tinnitus has no cure, that is known, right? So one recommended treatment is that you sleep next to a noise machine.
Wow.
Something that makes white noise or ocean waves or something, one of those machines. And the explanation usually given is that will distract your brain from thinking about this buzz that you're hearing. But there's another potential explanation in light of what we were showing, which is that the adaptive gain mechanism tunes down the gain when the input volume is loud. And so when you subject yourself to even louder noise as you have this buzz, you're tuning down the adaptive gain, which then puts you back in the stable regime. That's one explanation.
Okay.
If you buy that, then that gives you another idea. Now that you have a model, a mechanical model that you can then apply signals to, search for the open loop signal with minimal power that will turn down that adaptive gain mechanism. So you don't have to have just white noise that, you can maybe have a much more intelligently designed signal that's not quite as loud as what the noise machine is producing, but has the effect of turning down that adaptive gain mechanism. And already you can kind of see from our analysis that there's a certain frequency band where you need that signal. You don't need it in all frequencies, because the adaptive gain mechanism is tuned to a particular range of frequencies primarily. That's one idea. The other more intriguing idea is if it's true that this is a spontaneous oscillation from a mechanical instability in the cochlea, then implement the feedback controller in a hearing aid. So the hearing aid will sense the vibrations of the eardrum acoustically and will provide feedback that then interferes with that dynamics. So in some sense, you're providing an active acoustic impedance right here that will dynamically interact with the cochlear membrane motion and stabilize it, potentially. So you actually stabilize the instability with a feedback.
Amazing.
So these are all open questions, but that's what the analysis sort of implies you can do.
I'm looking forward to seeing those devices in the wild. I'll think about you when I happen to see them. Very, very fascinating.
And by the way, I am, I'm not a medical researcher, so this is all speculation on my part.
Sure, but an extremely interesting and informed speculation, at least informed by control. Fantastic. Again, another completely orthogonal topic, but somehow related to, multiplicative noise, since you mentioned it. So recently I read up this paper with Roy Smith here at ETH, and I found that also particularly interesting because it's about how do we measure basically performance, but in certain types of stochastic systems where we have stochasticity in the feedback loop. It's a paper that appeared on Control Systems magazine, Stochasticity in Feedback Loops, Great Expectations and Guaranteed Ruin. Why that title?
So this, again, is a system with random multiplicative noise, but it's a it's like the simplest system you can imagine. It's just discrete time, x at time t plus 1 equals a of t times x of t. A of t is a random with a given distribution that you can experiment with. And so we wanted to see the simplest manifestation of this problem. So a linear system with additive noise, let's say the additive noise is Gaussian. A linear system will produce Gaussian results, and you can analyze the variance and the mean using standard techniques. But when a noise enters multiplicativity, when it multiplies the state, essentially all bets are off. I mean, in the sense that the behavior can be very, very rich, even though it's linear dynamics. And by the way, maybe this is something we can address later on, the distinction between linear and nonlinear dynamics, which is something that I've done some thinking about. But this system can have quite rich behavior. And so Roy Smith and I were talking about this, and we were experimenting with this. And so we looked at a case where you can tailor the probability distribution of the parameter A. So even if A is Gaussian and X is Gaussian, you're going to end up with non-Gaussian distributions. And so we looked at a case where we can rig up the distribution of the parameter A such that you can have the mean is unstable. So the mean of the state in the single system, the mean is unstable, so it's growing geometrically, this is discrete time. But you can show that with probability 1, every trajectory goes to 0.
That is very, very difficult to digest.
Yeah, but the distribution has to be just right. So, the condition is that the analysis is really simple. So because it's a scalar multiplicative system, you can take logs and then it becomes an additive system, and you can analyze that way and then take exponential again. So you can actually get a precise condition for the stability from every sample path. It turned out in these problems that what you have, there are two ways to understand it. As t goes to infinity, you're converging to a distribution that's bunching around 0. It's becoming more like a delta function. So with probability 1, everything is going to 0. But at the same time, the mean is growing. So if you think about it, maybe an appropriately chosen limit, you are going to a distribution that has no mean, has infinite mean, like a Cauchy distribution or something like that. But it is actually looking very, very bunched up as t goes to infinity.
Okay.
This was not new. Back in 1963, Carl Ostrom wrote a paper in continuous time for a scalar system where he analyzed similar phenomena. So then he solved the Fokker-Planck equation for that system and showed that the distributions in certain cases have this behavior. we did a much simpler analysis where you can sort of exactly find what the distribution is. Another interpretation, which maybe gives you more intuition, is that every trajectory is going to zero. But occasionally there are these rare events where some trajectories jump high and come back down. But because they jump so high, they actually make the mean big. These are the rare events, heavy tails that occur, which are enough to make the mean grow. And then Roy came up with this financial sort of interpretation where they say, I will sell you an investment strategy where I guarantee you that on average, your annual return is 5%. Guaranteed, because the average, over, let's say, 1 million people who invest in this, is going at 5%. But with probability 1, your portfolio will go to zero. That's T goes to infinity. So that's the guaranteed ruin. And then the great expectation is because the expected value is growing at 5% every year.
And also the article seems to make the case that the median is actually the correct thing to look at.
Yes. So the median behaves like every sample trajectory. Yes. So, yeah.
There is this plot in the end of the article that is somewhat, at least for me, it was somewhat surprising or unintuitive, where you see that the median seems to behave well, whereas the mean, as you say, explodes.
The mean does not behave well because the mean itself is blowing up. In fact, if you just run a stochastic simulation, you run, many thousands of samples, and you try to calculate the empirical mean, you will see that it's very noisy because, again, it's not converging to a finite number. So the mean itself fluctuates significantly, even though its expected value is growing. So even if you try to empirically measure the mean, you will see that there's a lot of noise in it. And you keep increasing the number of samples, and that noise doesn't go away because you're converging to a distribution that has infinite mean.
So this seems to be another defining thread of your journey in control. So we're steering people's attentions from the wrong quantities to the correct ones.
Yeah.
In this case, the median rather than the mean.
Correct. Yes. Yeah. I mean, again, you have to rig up a system to behave like that. There are other examples where you don't have this kind of behavior. But Roy wanted to write a paper to say, well, be careful. This is something that could happen in your system.
Okay, this is bringing us very, very close to basically today in time. I was wondering, what are you studying? What are your interests these days? And what are your thoughts also on the future of control theory as a whole?
Well, so I'm interested in maybe too many things. So I'm still working on, distributed control problems in various aspects of it, and synchronized oscillators and other problems, and PDEs and the performance limitations. Again, the architectural issues are really what concerns me most. I think in terms of control theory as a field, I wanted to say this, like, ever since I was a graduate student in the mid-'80s, I kept hearing control is dead. Control is sort of a relic of the past. It's not so important anymore. It's not like an area that is at the forefront of research. And I heard that as a graduate student, and I said, I don't care, because I like the theory and I like the work, and I thought it was fascinating. I thought there were lots of open problems. But I think, this also goes to the way many textbooks in control theory are written. Control theory, as we kind of have seen it in the 80s and maybe till today, is very much influenced by its heritage from aerospace applications. In fact, most textbooks really are formulating control problems primarily for use in aerospace problems. And I think that's too limiting for the theory as it exists today. There are many other problems not in aerospace. Distributed control is one of them, but there are probably others in biology, for example, where that aerospace-motivated formulation isn't really the best one. And so we need to formulate different problems and ask maybe different questions. Architectural questions, of course, are one of them. And I think that's kind of the future of the field, rather than sort of thinking of control theory as the textbooks that were written in the 60s and were sort of tied to that view of the field originating from aerospace. So I see that, when you look at problems in biology or problems in distributed control or problems in physics, these are all open problems for control, but we need to develop, where people are developing these tools now. I mean, there's a lot of interesting recent work where people are developing tools for applications in these other domains. And we're trying to get out of this mentality of aerospace control.
Two things that you mentioned earlier were this tension between linear and nonlinear, and also the role of data. And
yes,
we're living in this age of information. Any thoughts in that regard?
Yeah, so one of my colleagues at UC Santa Barbara, Igor Mazic, has popularized this notion of the Koopman representation for nonlinear systems, which is becoming popular and now goes by several names like dynamic mode decomposition. I want to say a little bit about that, because I think this is I can make a very precise technical point about this. And it's been known for a very long time, since the 30s, for example. There is something called the Carleman linearization. That's Carleman, not Kalman. And then Koopman, around the same time, developed his representation. So these are universal models for nonlinear systems, but they are linear, infinite dimensional models for nonlinear systems. So you can take a nonlinear system, the Carleman or the Koopman linearizations, and these are, rather than call them linearizations, you should call them representations. So I can take a nonlinear system and then embed it inside an infinite dimensional linear system, in the sense that every trajectory of this nonlinear system I can extract from trajectories of the linear system, the infinite dimensional linear system. This has several implications. First of all, I'd like to say that these ideas have been around since the 30s, but many people have had similar experience to me. I discovered this as a grad student, and I was blown away. For like 2 days, I thought I can solve any nonlinear problem now, because it's a linear system, infinite dimensional nonetheless, right? And then you realize that you've run against the curse of dimensionality, right? So in some sense, the infinite dimensional linear system is much more complicated to analyze than the finite dimensional nonlinear system sometimes, right? And so quickly, many people we move on to other things, right? But there's an important point to be made here. When we speak of nonlinear phenomena or nonlinear behavior versus linear behavior, and that's something that I've had to confront many, many times, especially because of the work on turbulence, where people regard it as a fundamentally nonlinear phenomenon. And this idea of the Carleman or Koopman linearization gives you a little bit of clarity, because you think every trajectory that is generated by a nonlinear system can be also generated by a linear system. So what does it mean to say nonlinear phenomenon or nonlinear behavior? It really has no mathematical meaning, because the same phenomenology that is produced by a nonlinear system can also be produced by a linear system, even though it's infinite dimensional, right? So it makes you think, so these are different representations of the same system, and the boundary of complexity is not between linear and nonlinear models, it's something else. So that distinction I find to be somewhat artificial and unhelpful. Now, the Koopman picture is becoming very popular, primarily due to data-driven techniques. So I mentioned the curse of dimensionality. So to actually do true analysis with Koopman and Carleman is really intractable for the most part, except for very low dimensional systems, dimension 2 or 3 for the states fixed. But a lot of people are now doing this analysis in a data-driven manner. And I haven't been following all of the literature because it's really been exploding very rapidly. But basically, if you take data and you say, I'm going to identify the Koopman modes, what you're really doing is linear system identification. You're taking trajectories generated by a nonlinear system, and you're doing linear system identification, okay? And there are certain tricks people play. For example, if you don't use your original state variables, but you use maybe some polynomial functions of them, people call it dictionary nowadays, you might be able to do this linear system ID with a very low order instead of very high order. So that becomes kind of an art. How do you pick these polynomials? And I see that in other areas where I see people doing basically linear system ID, but with sort of nonlinear definitions of the state variables. or nonlinear definitions and input, when it goes back in the system ID literature to these Hammerstein models, for example, where you have a memoryless nonlinearity followed by an LTI system. And that can model a fairly large class of nonlinear systems. So again, the distinction between linear and nonlinear is getting very, very fuzzy, in my opinion, especially in the data-driven world, where linear models seem to be coming back again with modifications by sort of selection. What are the variables that you think have linear relationships? And then, work that was done, so this is becoming maybe more of a trend now, and one of my colleagues, Enoch Jung, has done this, where you have a nonlinear transformation, you can think of it as an encoder, and then you have LTI dynamics, and you try to learn both simultaneously. You're learning the nonlinear transformation and the LTI dynamics, which represents your nonlinear system. And that seems to be very useful these days. And very recently, there's the Mamba model for large language learning, which if you look at the architecture, it looks a lot like a state space realization, but it has some other nonlinear components, namely the dictionary that you associate the words with. But again, in the training, you're learning the dictionary and the linear dynamics simultaneously. And that seems to be a rich enough class of models that people can actually do useful things with it.
I'm not aware of this Mamba model. I never heard before.
It's very recent, it's very recent.
Sorry, I interrupted you.
No, I'm just saying, I think one of the most unhelpful ideas that have dominated our discipline for a long time is that there's a distinction between linear and nonlinear systems. And I think that distinction is at best artificial and really very misleading.
One could think of nonlinear models as compact representations of very complex but linear, very high-dimensional systems. One is a way to think about it, maybe.
Yes, I'll give you a concrete example. So in optimal estimation theory, the optimal estimator for most nonlinear systems is given by a PDE, the Zakai equation, it's called. So it's an infinite dimensional PDE that tracks the conditional density. And then that is your optimal estimator. Of course, it's a horribly high dimensional object, which you will run into the curse of dimensionality if you try to obtain it. In the Kalman filter case, this large high dimensional object, which is this PDE, collapses to the differential Riccati equation for the Kalman gain. Mm-hmm. But for the error covariance, which then gives you the Kalman gain. So that's an example of a linear. The Zakai equation I forgot to mention is linear. It's a linear PDE, curse of dimensionality, high dimensional object. In the special case of the Kalman filter, it collapses to the Riccati equation, which is a nonlinear differential equation.
Amazing.
Because it's a Riccati differential equation. And so that nonlinear differential equation is much easier to deal with than the original PDE for the conditional density. So that's an example where, nonlinear systems, as you said, are a compact representation of potentially an infinite dimensional object.
Wonderful. Well, actually, maybe this brings us to some of the questions that I normally ask to our guests towards the end of the episode. So one of them is related to your taste. So it comes from our audience. And this person asked me directly to ask you in this podcast, where I'm curious about how do you select problems that you work on and why, if there is any methodology.
The one way to answer this question is that, I'll go for a dichotomy, which I think most dichotomies are false, but sometimes they help sort of clarify things. So there are people whose research is motivated by a particular application, a particular problem that they want to crack. Say, plasma control in tokamaks, or blood sugar regulation in diabetes. These are problems that they will then take every tool that they can get their hand on and to attack that problem. So that's one extreme, if you will. The other extreme is, and usually it goes by the pejorative, that you have a hammer and everything you see is a nail. So you have a collection of tools, mathematical or computational or whatever, and then you look for problems to which your tools apply, right? Because you like using those tools and you derive pleasure from that. And that's these are two different research models. I think I tend to fall on the side of the person who has tools and enjoys using the mathematical tools, because I like to see structure, and the beauty of the structure is really what motivates me. But it's good to know that about yourself as a researcher. What is it that motivates you? And not listen to, somebody saying, well, the direction of the field is this way, or these are the important problems to be looking at. Because you get up every day and in order to be excited about what you're doing, you have to have that passion for it. And the passion comes from recognizing what is it you like doing, right? So that is the self, and that's different for different people. I myself am motivated by techniques and tools that I can use to solve problems. I typically have more than one, like a portfolio of problems to look at and see which ones pan out. Because I tell this to my students all the time, you can pick a research problem, but don't stick, if it turns out to be the questions you're asking, if they turn out to be very hard, don't spend 5 years banging your head against the wall trying to answer those questions that maybe they're very difficult to answer, or maybe they're not the right questions to ask. So keep the flexibility to try to ask many different questions and see which ones pan out. So it's almost like a portfolio model for research. Keep a diverse portfolio and see which one gives you good returns on your investment.
This is great because somehow you're addressing, well, first of all, the question that I asked you, but also the next question that I would have had for you. So if you wish advice to future generations, or one piece of advice, but also touches on the third question that I would have asked you, and that's, what would you invest on today if you were to be a student? So having this approach mindset, if you want, of financial investment for a future student.
In terms of investment, you can never lose by learning more mathematical techniques. That's, for example, I tell my students, I tell the undergrad students as well, is like, for example, linear algebra. Like linear algebra, though, understood in a very expansive sense as functional analysis and linear algebra altogether, is a vast topic, but it's worth investing in learning it really well and learning as much as you can. I always give the students who are in the graduate class this famous paper, which has never been published, but it's on arXiv, called the $25 billion eigenvector. I don't know if you've seen that paper.
No, I haven't.
That is a paper that describes the Google PageRank algorithm. And this paper came out maybe 20 years ago and describes how the PageRank algorithms can be expressed as finding an eigenvector for the eigenvalue of one of this large matrix that you form from the connectivity of web pages on the internet. And $25 billion was the valuation of Google when it went public. Thus the name of the... So the publication is trying to say your eigenvector may be worth $25 billion. So don't dismiss eigenvectors. Try to understand what they are and what they do. So one thing is, you can never go wrong with learning more math. Okay, and whatever flavor of math excites you. And, it's a cliche, but just follow what you're really interested in, because doing a PhD or being a researcher is not like being a student, because many times things don't pan out, or you may not get the results you think you should get. So it's a labor of love. You have to actually love it every day. Otherwise, your life is going to be miserable. So select problems and select the research that gives you pleasure every day, because you're not quite sure when things pan out and when they don't, and you don't want to, or that should not be your measure of success. So your measure of success should be, am I enjoying doing this research? Regardless of whether the results are going to be fantastic or they're going to be mediocre, that's kind of secondary to the daily enjoyment of what you're doing.
It's great to hear this also from a person like you who has had so many brilliant ideas. It's amazing. Maybe one last question before we close this episode, and that is regarding the future again of systems theory. Where are we heading? And what is, in your view, very tough to solve?
Okay. As I said, I view controls as an evolving field, not as a mature field. People think, well, control theory is a mature field by now. I don't think that's true. I think it's still evolving. As I said, there are all these new problems from biology, machine learning, physics that are begging for, people come to us from biology, from fluid dynamics, from other areas, saying this control theory it sounds very intriguing. It sounds like it would solve my problems. How do I learn about this? And then we give them these horrible textbooks and they say, here's control, you go learn that. And then they can't really make much of it. So the onus is on us to try to make contact with other fields and try to evolve our own mathematical problem formulations so that it makes more sense for the problems in the other fields and not be stuck in this aerospace heritage, which is great for certain things, but certainly a very narrow way of thinking about control theory in a much more expansive sense. There are interesting problems now in machine learning, in my opinion. You can think about the contact between machine learning and control theory, which a lot of people are thinking about. One way is to use the techniques of machine learning to design controllers or control algorithms. So reinforcement learning, data-driven, et cetera, et cetera. There's another direction which I think is less appreciated, but I think probably more interesting, which is to use control theory and system theory notions to understand what's going on in machine learning. The machine learning algorithms, they're intriguing instances of this. I mentioned the Mamba architecture earlier. There's another problem, which is diffusion models for generative AI, which basically amount to generating or sampling from these very high dimensional distributions to generate sort of artificial pictures of cats and dogs and fish and so on. So the common technique is these image diffusion models. I won't describe it in detail, but basically I'll just to say that one of the main references, at least for the people who kind of know a little bit about the history of this, is a 1984 paper by Brian Anderson on stochastic differential equations and how you go from one distribution at one end over several stages to the other one. And then how do you go backwards, which is reversing this stochastic equation in a stable manner. And this is essentially the basic idea behind these diffusion models for generative image generation. And it's related to spectral factorization. I mean, at least Brian Anderson relates it to a finite horizon version of spectral factorization. If you think about spectral factorization, it's really kind of a generative AI, if you will, right? So generate for me a stochastic process with a prescribed power spectral density, or from a prescribed power spectral density. Generative AI for image generation, they're generating a sample from a very high dimensional distribution of images. In spectral factorization, you build an LTI filter that when you feed it white noise, out comes a process with the prescribed power spectral density, which has the tonality, if you listen to it acoustically, it has a certain tonality that's unique to it. In diffusion models, you generate a picture, an artificial cat, by putting in a white Gaussian random field at the end of that diffusion process, and out comes a picture of a cat. So in a sort of at a high level sense, they're really the same problem. And so we could think about all of these problems in machine learning in terms of using control and systems techniques. Of course, that's already been done by Laurent Tessard and Ben Recht and others who have used basically IQCs in order to analyze various optimization algorithms that people use in machine learning. So I feel that direction of research is really quite interesting and quite, there's a lot to be done there. Don't try to just copy what the machine learning people are doing. Try to solve the problem that they cannot solve yet, which is explain what's going on in these machine learning black boxes.
Amazing. I never thought about the connection between spectral factorization and generative models. That was really, really fascinating to follow.
It's an early form of generative AI.
It is. And the cat that we're producing is the impulse response, of some system somehow. I never thought about it. Fantastic. And perhaps also the robustness questions that I don't hear. Well, I do hear it in machine learning, but not as much as I think should be.
Yes. I mean, there are a lot of unsolved problems in machine learning, right? And another way to think about it is that the machine learning community has been engaged in a lot of computational experimentation. So it's like a comparison to physics would be like around the turn of the century, the 20th century, there were a lot of physics experiments that where there was no theory to explain what's going on in the experiments. And then physics developed the relevant theories to explain all of this large body of experimentation that produced puzzles. And so what we have now is a large number of computational experiments in large language models and other machine learning, which are producing fascinating results for which there's very little theory to explain. And so we're in that similar situation where, it's crying out for explanatory theories. And it's a scientific opportunity.
I fully agree. And since you mentioned physics, I have to ask you this last question again from our fans that reached out, knowing some of our fans knew that I was about to interview, and it relates to the number of physics books that you have in your office, apparently. Some people tell me that you have an immense amount of physics books, and I'm wondering why.
I've always been my undergrad was physics and electrical engineering, and I was very close to going to grad school in physics. So I've always been interested in physics, and I still have that. I'm glad I did not do graduate school in physics, that I did it in engineering, because in a way, physics education has a lot of history, and there's a lot of orthodoxy in physics education, much more than engineering. Engineering is kind of, like everything goes. And so there's a lot more room for asking different questions, thinking in different ways, that I feel somehow maybe the physicists are sort of tied with sort of the baggage of the history in their field. But physics is fundamentally interesting to me, and I love physics. And that's why whenever I can connect my work in controls with physics, I jump on that opportunity.
And that is very evident from the curriculum. Well, Bassam, this brings up to the end of this episode. It's been a real pleasure to have you with us today. Thank you so much.
Thank you, Alberto. Thank you for having me. And again, I'm really enjoying listening to all of your podcasts, even the ones with people that I thought I knew quite well, and I thought I knew their papers. But when I hear them discussing them on your podcast, I see some new insight that I have not seen before. So thank you for asking the good questions.
Thank you for listening. I hope you liked the show today. If you enjoyed the podcast, please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time.